I've had some questions about problems 5, 6, and 8 from chapter 31. So I thought I'd do a quick walkthrough on those since well, it's 5 o'clock the night before the test. So let's talk about 5 first. You have here ionizing radiation deposits 1.22 MeV, right? So we've got 1.22 MeV in the gas of a Geiger tube, and it creates ion pairs, and each ion pair takes 33.4 eV, right? So we've got 33.4 eV per pair. That's one way to think about it, right? And we want to know what the current is if it dissipates in 1.3 seconds. Well, if we take 1.2 MeV, right, 1.22 times 10 to the 6th, right, EV, and we divide it by the 33.4 EV per pair, that's going to end up being this number of pairs, right? So now we know how many pairs we have. Once we know how many pairs we have, what do? Well, each pair has a charge that goes with it that's equal to the charge on the electron. So the number of pairs, right? Number of pairs times 1.6 times the number here is 10 to the minus 19, right? 1.6 times 10 to the minus 19 coulombs is going to give us the charge, and the charge divided by the amount of time it takes to dissipate is the current, right? So we take our MeV of energy deposited, we take the EV of energy per pair, sort out how many pairs we are, we take the charge per pair, sort out the total charge, we take that total charge divided by the amount of time, and that gives us the current. Okay, so that's number 5. Number 6, all right, we have what is the fraction of a sample of 40 potassium 40 remains after 3.82 times 10 to the 9th years, right? State your answer as a percentage. Okay. So one of the things we need to know for question number 6 is the half-life of potassium. So let's go to our P table. All right, let's go to our P table. Let's pick up potassium. We're after potassium 40. It's right there. We can't quite see that. Let's see if I can make that big enough that we can see it. Potassium 40 in the P table has a half-life 1.251 times 10 to the 9th years. Right? That's the half-life for potassium 40 from the P table, 1.251 times 10 to the 9th years. Well, now we know the half-life, right? So we know T sub 1/2, right, is that 1.251 times 10 to the 9th. All right, 9th years. We know T sub half, right? We know the half-life. Well, from the half-life, we figured out lambda, right? Once we have lambda, we know that we have N equals N. Let me do that. Once we have lambda, all right, we know that we have N equals N naught E to the minus lambda T, right? So we use the half-life of potassium to find lambda right there. We're given the time T right there. Now, we don't know N naught and we don't know N, but we're not asked for those. We're asked for what fraction remains. If you start off with 10 apples, right, and you've got 3 left, what fraction do you have left? You have 3 tenths left, right? So we start off with N naught potassium atoms, and after time t we have N left. So the fraction we have left is N over N naught, right? Fraction we have left is N over N naught. And then you just convert that to a percentage by multiplying by 100. All right. And number 8. We got uranium. We've got 1.016 milligrams, the relatively scarce uranium. We need to find its mass. Find this mass, and finds this mass to have an activity of 78.4 becquerel. What is its half-life in millions of years? So we're going to take first this 1.016 milligrams. We're going to convert it to grams. All right. How many grams is that? Well, this is 0.001 grams, right? So we have 0.001 grams of 0.001 grams of uranium. It is uranium-235, so we have a mole for every 235 grams, right? Times 6 times 10, so you can do all this conversion to get the number of uranium atoms that we actually have, right? And we know the activity. We know the activity in becquerel. The activity in becquerel is 78.4 becquerel. And so the activity, right, in becquerel equals 0.693 over the half-life times the number of atoms. Okay, so in this instance, we know R. That's the 78.4 becquerel. We don't know T sub 1/2. And so we're looking for T sub 1/2 is 0.693 over R times N. We know N from up here. So N over R times 0.693 gets us to the half-life, right? And to get the half-life, becquerel, half-life in millions of years. So once you get the half-life, you're right, a million years is 10 to the 6th. So you divide by 10 to the 6th to get the half-life in millions of years. And that's it for problems 5, 6, and 8. Hopefully this helps.